Okay, I've listed 17 areas, which are fairly comprehensive over what we've done in the course, but I've probably forgotten some things. We'll talk about them next time. But number one is parametric curves. Number two is parametric surfaces. Number three is line integrals. Four is surface integrals. Five is integrals over plane regions. Six is integrals over three-dimensional regions. Seven is gradients, divergence, and curls. Both, how do you do them? And do you understand what they're telling you? Number eight is conservative fields. Number nine, motion along the curve. That's like tangent vectors, acceleration vectors, unit tangent, unit normal, unit binormal, tangential and normal components of acceleration. Number 10 is circulation integrals. Number 11 is flux integrals. Number 12 is Green's theorem. Number 13 is Stokes' theorem. Number 14 is the divergence theorem. Number 15 is conic sections. Number 16 is quadric surfaces. Number 17, general need for review. And I'm going to put a number 18 there. That could be anything I didn't list. And I would like you to specify that. Okay. If there's something I didn't list, let me know what it is so I can be sure to consider addressing it. Okay. Okay. So we've rated these things. As expected, the recent stuff, flux integrals through the divergence theorem, were rated pretty high on the need for review. Since I haven't gotten all the homework, I've gotten most of it, but the last assignment I've only got maybe from half the class. Okay, so get it to me before Thursday so I can do a better synopsis. Okay, because all the rest of this stuff feeds into this. I see parametric curves and parametric surfaces, especially the surfaces, parameterizing curves and parameterizing surfaces. I would have anticipated that was a need. So we want to talk about that. We do need to talk a little bit more about surface integrals. You're okay once you have the parameterization. You can do the TU cross TV and pretty much use it correctly, but you still need maybe a little work on how understanding how that all works. Okay. And especially, are you integrating a scalar over the thing, in which case you do the magnitude of TU cross TV, or you're doing like an F dot and, F dot normal times your area, in which case you use the whole vector, because if you didn't, you wouldn't have anything to dot with. Okay. And it's pretty obvious just from the syntax of the thing when you need to use the vector TU cross TV and when you don't. Okay. Integrals over plane regions. I mentioned that I did a video last time over some of the most basic things. So I'm not going to talk about that until you've had a chance to look at that video. I don't know if you're going to have time to look at that video, because I understand that you have other classes. I didn't know that. I was thinking this is the only class everybody was taking. No wonder you have that hollowed out look in your eye at this point of the semester. No, actually, y'all look pretty good, considering what you've certainly been through in an engineering curriculum. Okay. And integrals over plane regions. Well, that's what I just talked about. And I don't want to talk about integrals over three-dimensional regions until we at least had a chance to take at least a glance at the basics of integrals over plane regions. So whether you glance at what I did or not, try to be sure you understand this, so it makes it easier to understand the integrals over three-dimensional regions. gradients, divergences, and curls are just using the del operator, right? So I'm going to make all the del operator as far as doing calculations. And I don't see anybody really having problems with calculations. Okay. But what do you understand? Okay. Do you understand that the curl is perpendicular to both vectors by the right-hand rule? Okay. And that's real important. If you try to do the surface integral of the normal component of the curl, which is involved in Stokes theorem that I'm not going to talk about today, but you got to know where the curl goes. Okay. And how it's related to the normal to the surface. Okay. Okay. Conservative fields. The main comment that I want to get down here is that the conservative field is the gradient of some scalar field. And the scalar field is called the potential function. An example of that, if the field is the electric field, then the potential function is the function that gives you the voltage. Okay? The voltage function tells you the voltage of each point in space relative to some point that you fix arbitrarily. It's like you got an integration constant or an F and so forth. Now, I'm not going to get into electric fields and stuff like that. If you do that in physics, you understand it, hopefully. But that's just an example of a field. Motion along a curve. People tended to feel pretty confident in that. I'll write a few things down, but just saying it kind of quickly. You've got your R vector. Then you got your dr dt, which is your velocity. The dr dt divided by magnitude gives you your unit tangent vector. Unit tangent vector is very handy. Gives you your direction of motion. Okay. Then you can take the derivative of your unit tangent vector and it gives you a normal vector. Okay. Normal vector toward the outside of the curve, wherever you happen to be on the curve. It's the vector in which direction things would slide on your seat if you're going around that curve. Okay. And then you got to divide that by its magnitude, and that gets to be a big calculation. One you should be able to do, because if you can do that calculation, you can probably do about any calculation with derivatives. Okay. Kind of there's a word for it. Still a little bit sleep deprived, and the word is not coming to me. Yeah. Anyhow, it's a big deal. It's right in the tip of my tongue, but I can't. And the binomial vector is a cross product of T and M. Okay. Your acceleration tangent to the curve is acceleration in the direction of your unit tangent vector. Your acceleration vector is just a second derivative of your position vector, which is the R vector. Okay. Now, all those words are probably, if I can convince ChatGPT to give you pretty literal interpretation of this part. Okay. It'll probably do a good job. It might even improve some of the words I'm saying, although I don't know how that would be possible. Okay. You get your acceleration vector and dot it with your unit tangent vector. That's a component of acceleration in the direction of motion. You dot the acceleration vector with your normal vector, and you get the component perpendicular to motion. Alternatively, you subtract the unit tangent vector from the acceleration vector, and you get the unit normal vector. Okay? There are two ways to get it. I see people doing things like, to calculate the normal component, use a formula. Okay? Here's a formula. If you don't understand the details of that formula, just do a dot product. And preferably and to reinforce it, subtract the tangential component from the vector. It gives you the normal component. Okay? And I told you to do that earlier. I mean, I recommended that you do that. As long as you do it right, even if you do it by memorizing formulas, you're going to get credit. Okay? If you do it all by memorizing formulas rather than understanding what's going on, you're going to be less equipped to understand what all this is telling you in whatever field of engineering you're going into. Okay? It's okay. I mean, if I can do formulas and stuff like that, that's a foundation. Okay? It's not as good a foundation as a deeper understanding, but you've only got so many hours in a week. So do the best you can and manage your time as best you can. Okay? And, consider my advice. The one you really ought to listen to is your engineering professor. He doesn't tell you the same thing I'm telling you. Well, have a little talk with him. No, that's you got your field. So consider what I'm telling you, but do what you need to do. Okay, circulation integral. A circulation integral, as I said, is nothing but a line integral around a closed path. Okay, the closed path is a boundary of some surface. Take a basketball and slice it anywhere. That gives you a surface bounded by whatever slice, whatever path the slice takes. Okay, you could even slice it, along kind of a curved slice. You probably wouldn't want to try to integrate that, but you could cut it that way. And Stokes' theorem tells you that the integral of the circulation, the curl, the circulation integral is the tangential component of whatever your force, whatever your field is. Okay, integrate the tangential component around the curve, and I can write that down in, it's the integral over the curve. F dot T ds, or dr if you want. Okay. Yeah, and that would be F dot dr. I like to write F dot T ds. MT, of course, is a vector. Can't not if you don't have two vectors. Okay. So that's your circulation integral, your flux integral and stuff like that. I'm not going to write it down, but I'm tempted to write it down. A flux integral would be like a double integral of F dot N d big S over the surface. Okay. That S doesn't look much like an S. Use your imagination. Green's theorem. The homework people did in Green's theorem looked pretty good. Okay. It's fairly straightforward, especially because the text, well, actually, I have to look at your homework again. There's a series of problems that ask you to do the Green's theorem integral both ways. And most people did it just one way. Okay. In other words, do the area integral and do the line integral and show that they're the same. Okay. The area integral of qx minus py, the line integral of p dx plus q dy. Okay. So if you haven't done that, you probably want to, because I'm very likely, I can't assure it, depends on how the balance turns out, you know, because when I make up a final, I make it up way too low. In the 2 or 3 steps, I shorten it, grit my teeth and omit things that I don't want to omit, shorten problems that I don't want to shorten, and try to give you something halfway reasonable. Usually I don't quite get the halfway, but deal with it. Okay. Divergence theorem. Not going to talk about that today. Conic sections and quadric surfaces. The big thing I'm going to tell you about conic sections right now is just you do a rectangle. And it's two A here and 2B here. And you should know what A and B are. It's x squared over A squared plus y squared over B squared equals 1. I guess I'll write that down. I've got room. These are things you should know, but just things you want to, right there's a picture of it. Okay. And the origin's right in the middle. I'll put a dot there. I'm not going to carefully label everything. You should know that. Okay. Also, plus or minus x squared over A squared, minus or plus y squared over B squared equals 1. You've got a rectangle, same dimensions. You draw diagonals, those are the asymptotes. And then your hyperbola is either here or here. It's not both. And you can figure out which one goes with the plus on this one, minus on this one. And you figure out which one goes with the minus on this one and the plus on this one by just testing, is it possible for x to be 0? If it's plus x squared minus y squared, no, it's not. I mean, yes, it is possible for x equals 0. No, it's not possible for x equals 0, because y squared over b squared, negative y squared over b squared, can't be equal to 1 because y squared can't be negative. A and b are positive. Okay, but it doesn't matter if A and B are positive because it's A squared plus B squared. Y squared over B squared is positive. If X is 0, that can't be. And if Y is 0, X squared over A squared can't be 0 because negative can't equal 1. That's it. Then you know which hyperbola to graph. It's the easiest way in the world to graph hyperbola. Now, if these things are translated to where this is, instead of the origin, this is a point HK, then you're just shifting everything H units in this direction, K units, H units in the X direction, K units in the Y direction. And X becomes X minus H, and Y becomes Y minus K. There you have it. Now you got to do some algebra. You have the thing in an unfamiliar form. I'm probably not going to lay that on. It's just one of the things that I'd like to have on a test, but I can't make the test long enough to include it. Okay, I'm not promising I won't. I can always throw you a curveball that I'm probably not going to, but I won't throw you many of them. Okay. And then you have quadratic surfaces, which are just ellipses and hyperbolas and parabolas, which I didn't mention in this model. You should understand parabolas because you understand the graph of x squared and how it shifts and everything. And you figure out where the focus and directrix and stuff are if you need to. But I'm probably not going to go to that level of detail on the fly. It's another curveball that I could throw you, but probably won't. I'll pick at least one curveball. Huh? There are things that I just kind of want to do. Did they really know this? um, and you got to be careful. You won't know which one's a curveball and which isn't. Okay. Now that's just kind of going over this with just a few pictures and comments. So now I'm going to start going over it in a little more detail where I can write things out. Okay. Got it. Your R of t is going to be parameterized in terms of function x of t and a function y of t. Okay. One paradigm example is if you have a circle, then x of t could be the cosine of t, and y of t could be the sine of t, and that would give you a unit circle with a period of 2 pi. Okay. But you have other curves. It could be a curve on the curve y equals x squared. So let x equal t, let y equal t squared, etc. Integrate some function f of x times the magnitude of dr. That would be the integral of f of x. Magnitude of dr is square root of dx squared plus dy squared, which is the integral of f of x times the square root of x prime dx plus y prime dy. It's x prime dt, x prime dt. And it's each of these is squared, which comes down to x prime squared plus y prime squared. And dt squareds factor out, take the square root, you get dt. There's your line integral of f of x over the line. Okay? That's the most concise way to understand it, and why you get that square root of x prime squared plus y prime squared, which is often written dx dt squared plus dy dt squared. The prime is implicitly the derivative with respect to t. Make sense? That should be familiar to you. But whatever you think about line integrals, if it isn't, equivalent to this, well, let me know about it. Okay? If you think it isn't equivalent, you might be right. There might be something I screwed up here. Okay? I don't think so, but maybe. And then if you got the integral of F dot dr, okay, that's a line integral of a, well, that's the tangential. That's the integral of x prime dt plus y prime dt. Okay, you know, I haven't written out the dr equals dx dt I plus dy dt j times dt. But you should understand that. And if you don't, email me a question or something. I'll talk about it next time if I can. Okay. X dot x prime dt plus y prime dt is just, and I left my I and j vectors off. There's an I, there's a j. It's x prime dt times the I vector plus y prime dt times the j vector. Because if you take the derivative or the differential of this thing with where x is the I component, y times the j, you're going to get the I and j components down here. So that might be a little hard to read, but that's what you've got. And that becomes x prime I plus y prime j times dt when you factor out the dt. And that's just the integral of f dot your unit tangent vector dt. Okay. No, not quite. It's the integral of f dot dt f dot your unit tangent vector times the square root of. No, chalk. That wasn't the chalk, that was me. Might be a little hard to read, but it's that times x prime squared plus y prime squared, square root of x prime squared plus y prime squared. And I'll make a little note over here. X prime I plus y prime j. Well, your unit tangent vector is this over the magnitude of x prime I plus y prime j. What's the magnitude of x prime I plus I prime j? It's x prime I plus y prime j divided by the square root of x prime squared plus y prime squared. Now I'm saying these as I write them because they might be hard to read because I'm trying to cram a lot of stuff onto the board. This means that f dot x prime I plus y prime j is f dot t, or unit tangent vector, which has a magnitude of x prime I plus y prime j, or square root of x prime squared plus y prime squared in the denominator. Well, this one doesn't have a denominator, so you better multiply the unit tangent vector by that denominator, which gives you this. And there you have it. Okay? Now, you probably ought to look at that until you got it sorted out, because you understand what I just said. You don't have to memorize as much stuff, and you're less likely to screw up something you memorized wrong. Okay? And it's really pretty important for understanding what a line integral is and what it tells you. You can do it without understanding it. Try to do it with understanding. You tend to do better on tests if you understand more deeply, and it tends to stick with you after the course, which we find to be always been universally a problem from one course to the next. Okay? Prepares you for being able to use this. Okay, well, enough preaching. That's kind of a summary of the line integral of a scalar function f of x over a curve, or a vector function over a curve. Now, the curve, I've suppressed it because I didn't want to get into a lot of detail, but the curve is defined over some t interval. A less than or equal to t less than or equal to b. So each of these integrals goes from a to b. You're not going to be able to read my A's and B's down here low on the board, but try to have a good imagination. It's always an integral from A to B. Picture of a line integral is here's R of A, here's R of B. You partition it. You take your typical interval of the partition, which has a sample point and a tangent, unit tangent vector. I'm not going to draw everything in here. It all starts with the fact that on the ith interval, the value of your scalar function, think of a density function, your density on this interval is going to just be the density at some point in the interval, some random point in the interval, multiplied by how long the interval is, okay? Number of kilograms per meter multiplied by your number of meters. Or I made an unfortunate notation here. I mean, this curve is presumably in space someplace. And, you know, if you have z components, you just add a dz squared here, right? Because if you have three-dimensional curve, you're going to have a z of t times k, right? There's a zk, z of t times k, then your dr is going to have three components. You're going to have a square root of dx squared plus dy squared plus dz squared. Everything else is the same. It's just that you've got one more thing to include your integral. Okay, so this should be there shouldn't be a star in this. So evaluate f at ti star, where t is the parameter that you're using to parameterize the curve. It could be t or s or u or v. You know, you choose what to call your parameter, but you partition the interval from A to B. The partition looks kind of like this. A equals T naught, and that's less than T1, which is less than T2, yada, yada, yada. Okay. And you get less than Ti minus 1, less than Ti. That applies to any interval here. And then you go on up to Tn minus 1. And Tn, when Tn equals B, you partition the interval into n subintervals. And that's what you're really doing when you do an interval. That's something that's really important to understand for applications. If you can't imagine what happens on a typical interval of a partition, then you can't imagine what the heck you're integrating. And you don't know what to integrate if you don't know what that thing you're trying to integrate is doing on an interval. Okay? Okay, so anyhow, you got then f of Ti star, where T is your parameter, dotted with I'll just do x prime I plus y prime j because I don't have room to write z prime k. It's in 3 dimensions, you would have z prime k. Okay. So, that's how you do a line interval. Okay. That's what it comes down to. It might look different with different notations. It might look different with different applications. But just ask yourself, what kind of function are we integrating? If we're integrating a vector function, we'd probably better either be doing the tangential component, that would be a circulation integral, or perhaps the normal component, f dot m. So I could maybe include that because that's pretty relevant to a whole lot of things. No, I don't want to do that. I have to generalize in 3 dimensions. I'll save that. Okay. So anyhow, that's a big deal. Okay. On a surface integral, you have 2 parameters because the surface is 2-dimensional. You don't have 3 parameters. A lot of you are trying to like put R and U and V into your surface integrals, all 3 as treating all 3 as parameters. Okay. Everything has to be in terms of U and V, or if you want R and T or whatever. Okay. 2 parameters. And you want to keep that straight. So make it's kind of a mental note of that. Okay. Don't want to look at integrals over 3-dimensional regions yet. Gradient divergence, curl. I wrote down one thing there. I want to talk about conservative fields. Write down a little bit more. I didn't notice any strong evidence of difficulty with the idea of conservative field or with the procedures. I want to make sure we understand the idea though. Del dot f is identically equal to 0. That's what that like triple equal sign means, identically. At all points, it's equal to 0. F is a gradient of some scalar function f. I haven't written the word scalar. It's implicit that this thing, which doesn't have an arrow over it, is a scalar function. Okay, f equals del f. F is potential function. The integral of f dot dr A to B. For R is parameterized in terms of some parameter, it goes from A to B. Yeah, I can write that. The integral from A to B. If big F equals del F, then del F is like an antiderivative of big F. So when you integrate from A to B of del F, you're getting F of B minus F of A. And I'm just going to say, you want to sort that idea out. Your book says it nicely. Other places say it nicely. Ask, in what sense is del F an antiderivative of a vector field? Okay, or something like that. What was I going to write? Yeah, it's what I said. Del F is like an antiderivative of your vector field big F. That's an idea you really want to carry around. Also, F of X, Y, Z can be obtained. You can actually get a formula for F of X, Y, Z if you integrate your vector field big F dot dr from some fixed point, which I call X naught, Y naught, Z naught, to the arbitrary point X, Y, Z. Okay, you do that integral, you end up with a formula whose gradient is big F. I think that was addressed in the text. I think that might have been addressed in the problem set. If not, just consider it to be enrichment. I think it's kind of an important thing. And if I didn't assign it in the problem set, it's my fault if you don't know it. Okay? There should have been problems that ask you to do that. And if it didn't assign them, might means the book doesn't even have them, which I would think to be a deficiency of the book. It doesn't have many deficiencies. So I suspect that maybe I just missed that one in the assignment. So don't worry about it obsessively, but it's just another connection that helps you understand conservative fields better. And the better you understand it, the better you're likely to be able to do on whatever I ask you in the exam. Okay. Motion along a curve. If it's a curve in three-dimensional space, you got an X, Y, Z. If it's a curve in 10-dimensional space, you probably have an X1, X2, X3 up through X10 functions of T as your parameters. And you can do the integral. You can do some integrals, at least just fine, line integrals. But what we're talking about, I got to keep looking back. Oh, heck. Did I do that? Did I really do what I think I did? I'm writing on the back of the board that I need to keep for reference. So I made a bad choice there. Okay, here we go. Again, x equals x of t, y equals y of t. Z equals z of t. Two things I didn't mention, I just wrote down to remind myself, we'll get to it. Your R vector is xi plus yj plus zk, where the t dependence is implicit. If you do motion, which you would be if t is time, then your velocity vector is dr dt, which is x prime I plus y prime j plus z prime k. The unit tangent vector is v over the magnitude of v, which is x prime I plus y prime j plus z prime k over the square root of x prime squared plus y prime squared plus z prime squared. Your acceleration vector is, I could write d squared r over dt squared, but I'm just going to write r double prime, which is x double prime I plus y double prime j plus z double prime k. I'm writing this quickly because this is all stuff I think you know, or at least will have clear if you just do a decent review of it. Because people did fairly well on this stuff. Okay? And then tangential component of the acceleration is a dot t. The normal component is just a minus the tangential component. Or, well, I'm just going to write that. You got a picture. You got a curve. You've got a unit tangent. You've got an acceleration vector. The component of the acceleration in the direction of the unit tangent vector, and I drew these vectors unfortunately. So I'm going to make that tangent vector a little longer so you can see what we're projecting. You project, and here in blue is, I don't have a good place to label it, but I'll squeeze it in here. There's your component of acceleration in the direction of the tangent vector. That should be a pretty obvious picture to you. Then you have the inward normal vector. In the component of it, which is perpendicular to your tangent vector, and it's toward the inward part of the curve. If I extend that vector so I can project the acceleration vector onto it, to be a dotted line. That's your component of the acceleration in the direction of the normal vector. These vectors are perpendicular. In other words, the tangent vector and the normal vector are perpendicular. And I did this in class, but your acceleration vector is the sum of this and this, because this is a rectangle, and there's your diagonal. Now your book gives you a formula to calculate A sub n, and there's nothing wrong with that. Another way to get A sub n, well, it's just the derivative of your unit tangent vector divided by magnitude of that derivative. It's a bit of a calculation to do that, and it gets pretty messy. So you can actually calculate your normal vector by this formula, but this is really a whole lot easier and more geometric. Okay. Now it looks like we're just about exactly out of time, so I'll continue with this on Thursday. Think we have time about the topics that are coming up. I'll try to retain that board. And if you have questions in the meantime, please get them to me. Anything you don't understand. And I'm going to add to the list equations of lines and equations of planes. I'm not going to say too much about this. That would be 19.